Okay, so good evening, everyone. Welcome to today's session on probability and statistics. So I'm Naresh, a research scholar from the Department of Civil Engineering at IISc. So we have been having these sessions once in a week, and this is the 10th session. You might have had a probability and statistics session by some other scholar before this, but let me just go through the basic concepts and then a few problems. So I think we may not have time for many problems because this is a slightly big topic. But I hope in case you need anything, as I always say, you can post it in the Google groups. I will respond. So welcome to the session. Thank you for joining. Let us see today's topics. So we'll start with some basic ideas of statistics. How do we handle data? Just a minute. Could anyone confirm that it's audible, voice is clear, and screen is fine, right?
Audible, sir.
Yes.
Audible, sir.
Thank you. Thank you. So we'll start with some basic data. How do we sample data? What are the measures, mean, median, and mode, and also the variance? Then we look at the probability theory. So if you introduce randomness in data, how do we handle it? What are the various theorems? And this concept of conditional probability. We'll also look at some just formula because that basically this is for gate. So it will be helpful to have some permutations and combinations formula in the hand. Then random variables is a theoretical concept. It's a very useful concept. We look at it. There have always been questions from random variables in GATE, say 2016, 23, and so on. We'll look at probability distributions, and finally we'll have a regression analysis. So the reference for whatever I'm covering today is this famous book, Advanced Engineering Mathematics by Krasik. So you can refer to it. It's the last unit of this book, the last module of this book. It will be useful. So coming to data sampling, you know what data is. When we perform some experiment or when we collect some information, we call it as data, and we don't usually have access to. So we need first idea is we need to talk about this, the concept of a population and a sample. Suppose we are interested in finding how does the risk of say diabetic disease varies with the age of a person in Indians. So the population here is the group of the set of all humans in India, and that cannot be studied. What people typically study is they take a random sample out of a population. So this is basically sampling theory. When we have a very large number of uh, points, right? So every human being is 1 point because each one gives us the status, whether they're diabetic or not, and their age. So you have age as one variable, diabetic presence is another variable. And say you take the entire some country, it's a very big population, and you sample a few out of it, and then uh, we do our studies. So there are certain things called the properties, the parameters of a sample. So to study the population, we use a sample, and in what helps us bridge the gap between the big population and the small sample is the probability theory. So the parameters of the population are being estimated by some parameters of the sample. Some of them are, first let us look at it. So first you sample the data, you select a random set of points, and then you sample the data, then you sort them. Why do we sort them? So if you have say x1, x2 is some set of numbers, and this is say the age of people, and if you want to find out the median, you first sort them. So after sorting, you can assign frequency. So frequency determines, say if suppose this represents the age of people in some sample, you would plot the number of people versus for every age versus the age itself. So this is basically a frequency. Say if you have x1 is equal to 10 years, x2 can be 11 years, x3 can be 12 years, and so on. So this is a discrete sample. So you can have in a you can have some number of people with 10 years of age, some number of people with 11 years of age, some number of people with 12 years of age. So the number of outcomes or the number of instances corresponding to every data point is called the frequency. So these are basic things. And you can also have what is called the cumulative frequency. Is total, that is nothing but the total number of people. So that is the total number of people with the age, the parameter less than or equal to your specified, say xn, xp or something. So you specify. So if you ask what is the frequency of the age 11, you just see how many people are having the age 11. If you ask what is the cumulative frequency of age 11, you need to add up all the ages from 0 to 11 and then report it. So that is the cumulative frequency. But these all are various representations of data. This is the discrete form, which is just listing. This is a more grouped form where you find out how many instances of every variable are there. Then to characterize such a distribution is not easy. So what we mainly use is measures of average and spread. If you have a very small sample, such as the number of students in a class, you can always arrange their ages in a ascending order or descending order, and then find the middle value. So that is some sense of a middle value. So the first measure of average or the first measure of a central tendency we'll be looking at is median. So median is nothing. This, as you would have studied in your school days or basic BTech, it is just the middle value in a discrete distribution. And in a continuous distribution, it is the 50th percentile value. We'll see what 50th percentile is. So if you have a discrete, say if it is just the, if you're just reporting the age to one, just as to 1 year accuracy, you will just have a discrete distribution. You cannot have a person of age 10.5. We don't report it. We just report it as 10 or 11. So corresponding to every number, every integer age, you have one frequency. So you can arrange them in a ascending order and you find the middle value, what separates the first n/2 values from the next n/2 or so. So that is the median. But if you have something like the height of people, that is having a continuous distribution. If you report it in centimeters or so, you have a continuous distribution. In that case, we'll identify what is called the 50th percentile, which is exactly the same as the middle value. Only thing is, how do we determine it is slightly different. We'll be looking at it very soon. The second is mode. What is mode? It is the maximum occurring value. That is obvious, so you don't need any explanation. You find out which data point is repeated multiple number of times, that is the mode. Most number of times, that is the mode. And the last is the mean. This is the most sophisticated one. So for a discrete sample as this, you know very well, the mean is, we have n number of data points. The mean x bar is defined as 1 by n summation of xi from as I goes from 1 to n. Now note that this is the mean of a sample. We'll also be looking at mean of a probability distribution that is entirely different from this. So the mean of a probability distribution is something to do with the population itself, and the mean of a sample is something to do with the sample points. Next, these are all measures of central tendency. How say average value or the middle value. So you can identify. So these are all kinds of kind of something which is tending towards the middle. But that alone is not essentially characterizing your data. If you take a classroom, you can have people of medium height, very small, very short people, and you can also have very tall people. Just by knowing the middle height or median height or the average height, we cannot get the extremes. So to characterize the extremes, we have another quantity which is called the variance. Again, what we are discussing here is the variance of a sample. So now that we have defined x bar as the mean of a sample, let us define what. So if x bar is the mean of a sample, and then the variance of a sample is defined as s square is equal to 1 by, if there are n sample points, say n students in a class, it is defined as 1 by n minus 1 times summation I going from 1 to n xi minus x bar the whole square. So you take every individual height, subtract it with the mean, square it, and add them all up. So finally divide it by n minus 1. So this n minus 1, the reason this n minus 1 is there is just because it works well in when the sample is very small compared to the population size. So for a very large population, if n is very large, it doesn't make any difference. 1 is very small compared to n. If you put it as n or n minus 1, makes no difference. So this n minus 1 is just to improve the accuracy in the case of small samples. So this is the variance of a sample and the standard deviation of a sample. So this is S square, right? This is a square quantity. You can always see this is greater than or equal to 0. So S is defined as the standard deviation. So that's all. These are just basic ideas of statistics. Let us quickly look at some problem. Very simple problem. We are not going to solve for anything, just qualitative thing. So you can look at, I hope the slide is visible. I have shifted from PDF to PPT. So you're given 4 probability distribution functions, right? So we have not looked at probability distribution functions so far, but just think of them as some frequency distribution charts, right? Just break them up into some bar graphs. So think of them as um, some frequency distribution charts, right? So instead of looking at the continuous curve, look at it as you have x as some variable, say age of a person or some height of a person, and the ordinate, the y-axis, represents the frequency. So we are given 4 such charts, and we are asked to find out what is in which of these the mean is greater than the median. So to approach this problem, you see, mean is something that has got to do with the average value. So for a probability distribution function or the frequency distribution function, the mean is something that is similar to a center of mass in mechanics, right? So it is that value. It is if you take the mean, that value is representative of the entire distribution as it is. So if you take the first function and the last function, you see they are symmetric about their center lines. So the area of the graph to the left side is equal to the area of the graph on the right side, both in the first graph and the last graph. Therefore, the median. So median, as I said, it is the 50th percentile value. What does it mean? It is that value x below which 50% of the sample points are lying. So that value of x below which 50% of the samples are lying. So you know that the probability, the area under the PDF gives the probability. So if you take the point at which the area is divided into 2 equal halves. So in this case, this is equal to this. So this line which I have drawn is actually the median, because the probability, or rather the frequency, is the relative frequency of the points below left side is 50%, and after this it is 50%. So for both the first and the second, the median is exactly at the middle. That is one thing. And what about the mean? So mean is an average value, and you can see that the average value is also in the middle. So how do you define mean? For a continuous distribution, mean is nothing but minus infinity to infinity x f of x dx. So this is called the expectation value of x, or the mean of x. And it is something like the moment of the probability density function. So f of x is the probability density function. You multiply that by x, and then you integrate. So this is similar to what we have, the moment in mechanics. So you see, where is the center of mass of the area? So this is just a trick. This is, if you're given the values and the probability distribution function as it is, you can evaluate it. But here we don't have anything. We are forced to estimate qualitatively. So here you use such tricks. You look at where the center of mass, qualitatively where the center of mass of the graph lies. So you can see in the first case, you can support it right here. So the center of mass is here. Here also it is here. Therefore, in these two cases, the mean and the median coincide. Look at the second case. You can see that this area is equal to this area. So the median is somewhere here. So this is just the same thing flipped. So here is the median. But will you be able to support this? Suppose you have a plate in this shape. Will you be able to support it by holding here? No, because the center of mass, the moment by this region will be greater than the moment due to this region, because this extends to a greater length. If it's of equal areas, this extends to a greater length. So the moment due to this region will be greater than the moment due to this region. Therefore, the mean is somewhat shifted towards this side. So mean can be somewhere here. And here it is just the opposite. So the mean is somewhere here. So we have already got the answer. Where the mean exceeds the median, it is option B, this one, where the mean is greater than the median. What about the mode of these? So mode is the maximum occurring value. So everywhere it corresponds to the peak value. So in all cases, you can say, so in the first case, this is the mode. In the first case, median and mode coincide. In the second case, the median and mode coincide. In the third case also, the median and mode coincide. In the last case, none of them, the mean and the median coincide, but the mode is different. So these two are the modal values. So this is just to motivate it. This is not a very, so this is just a simple problem. You don't have much to calculate in this. So I hope that is clear. We'll proceed with the presentation. So that is all it is. We have seen what mean, median, and mode are. In case of a discrete distribution, the mean is given as I said. The median is the middle value. Mode is the maximum occurring value, and variance is this one. It is defined as the sum of squares of the difference from the mean, and divided by the sample size -1. So next, getting into probability theory. So before we start the theorems, there are some basic ideas we need to know. One of them is the random experiment. What is a random experiment? So experiment is something that we measure or observe. So some observation, the act of performing some observation is an experiment. And why is it a random experiment? The results are not known with certainty. That is the only thing. So the random experiment has to do very much with the question we ask. Suppose you toss a coin and the question is whether the coin will fall down or not. That is, you throw a coin and you ask the question, the coin falls down or not. That is not a random experiment. That is an experiment with a known outcome. We know the loss of gravity, so the coin has to fall down. That's not a random experiment. That is an experiment. And you toss a coin and then you ask whether it will land on a head or a tail. That is a random experiment, because we don't know what, there is some uncertainty associated with what will be the result of the experiment. So I hope that makes it clear. What is a trial? Trial is one performance of a random experiment. So the act of tossing a coin is a random experiment. The act of tossing a coin and looking for what is the sign on the top face of the coin is a random experiment. One actual performance of tossing of coin and looking for the head or tail is a trial. It's a single performance of an experiment. Outcome is the result of a trial. So you do the experiment once and you see what is coming up. That is the result of a trial. So outcome can, if you toss a coin once, the outcome can be either a head or a tail. What is a sample space? It is the set of all outcomes. So from this point onwards, everything is mathematical. Up to this point, you know, it is some kind of mixed. It's just loose definitions. Once you define a random experiment, what is the trial and an outcome? Everything else is mathematically defined. There is no ambiguity from here on. So from the sample space onwards, it is a set. So that is a mathematical quantity, right? So the sample space is a set of all possible outcomes. So if your random experiment is to toss a single coin, what is the sample space of a single trial? The sample space of a trial is head or a tail. If your random experiment is to toss two coins simultaneously, and you perform one trial of this random experiment, what is the sample space? You can have either head and tail, tail and head, or tail and tail. So the sample space, the set of all possible outcomes, depends on how we define the random experiment, trial, and the outcomes. What is an event? Event is a subset of the sample space. So the sample space is typically denoted by S or omega. So an event A is a subset of the sample space. That's all. So event is, we can define event in a lot of non-mathematical manner, but with respect to probability theory, event is a subset of the sample space. It makes it is very helpful to look at all these in a diagrammatic view. So you perform one experiment, say you have a die and you toss it, you roll it, you roll the die once, that is a single trial, and you can have some set of outcomes, right? You can have some set of outcomes. The set of all outcomes, you can denote it by a diagram S. So this S is the sample space, and every outcome is called something called a sample point. And sample point is nothing but outcome of a trial. So these are all points in the sample space. You can take any collection of such points, right? As any subset of the sample space. So this three are existing both in the sample space and also in the set that I have denoted. So any subset of the sample space is called an event. And you can have a single outcome, a singleton set. So A can also be a singleton outcome. So you can take one outcome, and this is a singleton set, right? A set with just one element is called a singleton set. So a set of just one outcome is called a simple event. That is just to know. That's not very important. Then you can also define unions, intersections, and complements. So you know that very well. So you have A is one event. You can have B as another event. What is A union B? A union B is the set of all events E, a set of all outcomes, say E, such that E belongs to A or E belongs to B. So A is one event, B is one event. What is A union B? A union B is also an event. Let us call this event as E, which is a set of all outcomes in the sample space such that they belong either to A or to B or to both. So this is the basic set definition. And you can also have A intersection B, call that event as F. What is it? It is the set of all events F such that F belongs to A and F belongs to B. So, and what is complement? So you can say, you can define A complement is the set of all events, all outcomes A, which belong to the sample space, but they do not belong to A. So all these, let me mark in a different color. So these events, if you put these events together, that constitutes A complement. What are all the events that are not in A but are present in the sample space? Sorry, outcomes that are not in A but are present in the sample space. So these are all events. E is an event, uh, F is an event, A complement is a complement of event A, which is also an event. And you also know what are disjoint events. Disjoint or mutually exclusive. So you take A intersection B if it is the null set. So if this is say event C and these are event D, there is no common outcome for the two events. So those are called disjoint or mutually exclusive events. So these are just basic definitions. This is what the setup we need before we define probability. And how do we define probability? We have come to the main point. So there are various ways to define probability. What we have looked at in our class 11, class 12 is we would have defined probability in terms of equally likely outcomes. Suppose we toss a fair die. There are all the 6 faces are equally likely to land on the top. So the probability of an event A. Suppose the outcomes, so this relies on the, these are the basic three things we need for gate. We don't, there are also some other definitions, but those are not important. Suppose there are n equally likely outcomes for a trial or random experiment. Right? So you're performing a random experiment, and all the outcomes are equally likely. You have the sample space, and that has some number of, say, n number of outcomes, and all of them are equally likely. It can be tossing a fair die, tossing a fair coin, and so on. If they are all equally likely outcomes, then if they are equally likely, then the probability of an event A, remember we have defined event as a subset of the sample space, or which is some set of outcomes. So probability of an event A is nothing but the number of elements in A or outcomes in A. Our elements of the set A are all outcomes. So number of outcomes in A divided by number of outcomes in S. So you toss a fair die and you say the event A is getting a prime number on top. And what is the sample space of this event? Sample spaces, it can be 1, 2, 3, 4, 5, 6. What are the outcomes? So what are the outcomes which which is satisfying our condition? So the event A is nothing but getting a prime number, which is either 2, 3, or 5. Now, assuming that all the 6 outcomes are equally likely, by the first definition, the probability of A is the number of elements in A. What are the number of elements in A? It is 3. Number of outcomes in A is 3. The number of outcomes in S is 6. So the probability of getting a prime number when you toss a fair die is 0.5. However, this definition relies on the fact that the outcomes are equally likely. Suppose you toss a biased coin. Suppose you toss a biased coin such that the head occurs more number of times than tail. So you can assign, if you do the experiment infinitely many number of times, suppose the probability of occurrence of head is maybe say 0.75 and the probability of occurrence of tail is 0.25. How do we assign these probabilities? It needs to make sense, right? So this comes from the frequency distribution. Or rather relative frequency distribution. So you take a coin to find out if it is actually biased or it is not biased. With one trial, we can't do it, right? If I give you one coin, it can be biased or it can be unbiased. You're doing one trial, you're tossing it once, it will land either on a head or a tail. That is just one outcome. And similarly, you cannot, with that outcome, you can't say if the coin is biased or unbiased. Suppose I allow you to toss it 2 times, even then it is not enough. If I allow you to toss it 100 times, you toss a coin 100 times and say 74 times, 74 times it lands on a head and 26 times it lands on a tail. And another coin you toss such that 49 times it lands on a head and 51 times it lands on a tail. Which of these two will you call as a biased coin and which is an unbiased coin? By common sense, you will feel this is more biased and this is unbiased. So the next definition makes use of the relative frequency. So you perform a trial infinitely many number of times, not infinite, perform a trial large number of times. And you assign the relative frequency as the probability. So the probability of an event A is the number of times A occurs by total number of trials. So that is the second idea. These two are very different. Here you're performing the experiment. Here you know the likelihood. You know each outcome is equally likely. So even before even performing the experiment, you know what is the probability. Here it is like you need to suppose you do the trial very large number of times, and then you take the relative frequency, how many times an outcome in A occurs divided by the total number of trials. This is another definition of probability. But both of them have their limitations because some of the experiments we can't do a large number of times. Suppose we are looking at today's weather conditions, the temperature, wind speed and all. If we are asked to find out the probability of rain, right? You can see in say weather forecast, you have certain probability of rain, some percentage is reported, right? So that is not based on equally likely outcomes. It is not equally likely to have rain and not rain also. It is not based on relative frequency also, because today is just today. We have not had thousands of time. We have not seen today thousands of time before today, right? So it's not based on these two. It is something like axiomatic. So what does axiomatic definition mean is, so the probability of an event is a function. Is a function from what to what? Is a function from set of all events. So that is called the power set of S. Okay, but you don't need to know that. So you take the set of all subsets of S. So it is a function from a set of all subsets of S, which is set of all events, to the interval 0 to 1 on the real line. So you take every event and assign some number between 0 and 1 such that there are three conditions. So first condition as it has to lie between 0 and 1 for all events which are subsets of the sample space. The second condition is, if you take the sample space itself, its probability should be 1. So you can either have rain or you cannot have rain. There is no other outcome. So the sample space is the set of all possible outcomes. So that has a probability of 1. And the third thing is, if you have disjoint events or mutually exclusive events, A and B, then the probability of A union B is probability of A plus probability of B. Note that these two have to be disjoint. So these are axiomatic. Here we don't define probability, but what we say is, if you define probability, that should satisfy these three axioms. Axioms don't have proofs; they are just chosen in mathematics. So if you see why they have come up with this modern version of probabilities, it automatically satisfies both the above conditions and also certain other conditions. Say, for example, the rain or the likelihood of some disease can occur in future in a certain human being. So those involve this axiomatic definitions. So even this, once you know, this is how probability is defined. So A is an event. A complement is another event which is defined as complement of A in S. So we know P of S is 1. P of A is, say, let P of A can be some small p. What is P of A complement? We know A and A complement are disjoint events, right? There cannot be an outcome that is both in event A and it is not in event A. So A and A complement are disjoint. So P of A plus P of A complement should be equal to P of A union A complement. But what is A union A complement? That is, an outcome is in either in A or not in A. Means an outcome either is an event A or it is not an event A. What are all such outcomes together? That is the sample space itself. So it is P of S, which is 1. Therefore, P of A complement is 1 minus P of A. So this is the first result. The second result is just an extension of the last axiom. So if you have n number of events, A2 union AN, it is nothing but P of A1 plus P of A2 plus and so on up to P of AN, provided all are disjoint. All are disjoint. There is, if you take any two of them, there is no common outcome. And the last one is the most important thing. So this also follows directly from set theory. If you take P of A union B, here A and B are not necessarily disjoint, then it is nothing but P of A plus P of B minus P of A intersection B. So this can also be easily proven using the axioms of probability. You can also look at it from a Venn diagram point of view, right? So P of you have some number of events here, some number of outcomes here, and some number of outcomes common to both. So P of A will add up everything that is here. P of B will add up everything that is here, but you're counting this common area 2 times, so subtract it. So that is a Venn diagram kind of sketch, but the actual proof you can also do it rigorously from the axioms. But that's not very important from gate point of view. You can refer to Krayzig's book for that, or you can also post it to me. I'll give the proof later on. It's very small. It's just 2 lines. So let us look at some problem based on this. Okay, so this one was asked in GATE 2023 again. I think probably in set 1. So the probability of occurrence of 2 independent events A and B are 0.5 and 0.8 respectively. What is the probability of occurrence of at least A or B? Now we need to understand the question carefully. So state the given data. In probability, it always helps to. So in this case, they have not given what event A and event B is. Always start with the definition of event. And we do some other problem, I'll show. So A is what event? Say the act that the way I did. So you can define it as a prime number appears on the dice. B is an even number appears on the dice. So P of A is what? P of A is 0.5. P of B is 0.8. What is the probability of occurrence of at least A or B? So either A occurs or B occurs or both occurs, which means what does not occur? Neither A nor B does not occur, right? So either A has to occur or B has to occur. So if you take, let us take this rectangle to be the sample space. You have events everywhere. Sorry, you have outcomes everywhere in the sample space. A is one event. It has some outcomes inside. B is another event. It has some outcomes inside it. The probability of occurrence of either A, at least A or B lies inside this. Because this is event A, this is B. The outcomes outside this region, outcomes outside this shaded region, they do not occur. They do not correspond to event A or event B. So this is what we need. So what we want is P of A union B. So it is nothing but P of A plus P of B minus P of A intersection B. So P of A is 0.5, P of B is 0.8. What is P of A intersection B? We'll come to it, right? For finding P of A intersection B, we need to know what are independent events. So that is the next topic. So the next topic, so it's we need to look at what are called independent events. So independent events, as the name suggests, it means the outcome, the one event does not affect the, so the outcomes of one event does not affect the outcomes of the other event. For example, the fact that A has happened does not affect the does not affect the probability with which B will happen. So there is a special name to what we call as the fact that A has already happened. That is conditional probability. So what is conditional probability? We denote this as P of A condition B. Suppose you have two events. Let us take the same diagram. This is the sample space. This is an event A. It has some outcomes inside it. And this is an event B. It has some outcomes inside it. Suppose we know that the event B has already happened. Suppose B happened. We know this, right? If I tell you that if I tell you that B has happened, then what is the probability of A happening? Now, the idea is very simple. when we know that B has happened, then it means the outcomes outside B are not really valid outcomes, right? The set of all possible outcomes has reduced from the sample space to B. So B is called the new reduced sample space. So what do we do? To account for the fact that B has already happened, you divide by P of B. So this you can think of either in either of the two definitions. So in the first definition, you see the number of outcomes in S. Number of all possible outcomes was the number of outcomes in S. But now we know B happened. So B not happening is not a possibility. Whatever outcome we get has to be inside B. So instead of having 1 in the denominator, which is P of S, you have P of B in the denominator. And in numerator, what we have, it's not P of A, it is P of A intersection B. Why? The events in A that are outside B cannot happen. So this is conditional probability. If you know one event has already happened, then the probability of other event happening, provided that event has this B has happened, is P of A intersection B by P of B. Similarly, you can also define P of B intersection A, which is P of B condition A, which is P of B intersection A by P of A. At this point, we have something called the multiplication theorem, which says P of A intersection B is equal to P of B times P of A condition B. Just take it this side. Similarly, if you take it this side, it is also equal to P of A times P of B condition A. Now the important thing, yes.
Please repeat conditional probability.
Yes, sure. So conditional probabilities, maybe if I repeat with an example, it will be helpful. So you say, let us take the same dice example. So let me define the event A as a prime number appears on the top. Of course, the experiment is rolling a dice. It is a fair dice, and the trial is rolling it once and looking at the outcome on the top, looking at the number on the top. A is a prime number appears. B can be a multiple of 2, or what can be B? B can be, say, an odd number appears. Now, what is S for this event? It is 1, 2, 3, 4, 5, 6. Now I am defining something called, and you know, P of A is what? You can take either of the above definitions. So P of A is, what is prime number? What is A actually? A is at 2, 3, 5. B is 1, 3, 5. P of A is 3 by 6, which is 1 by 2. P of B is number of outcomes in B divided by number of outcomes in S. So again 3 by 6, which is 1 by 2. Now we'll come to this point of conditional probability. Now I have performed a trial. I've tossed, I've rolled a dice, and something has happened. I'm not telling you the outcome, right? If I tell you the outcome, then that is, you know, the outcome. The entire probability we're doing because there is some uncertainty associated with the outcome. Suppose I tell you nothing. I just tell you I have rolled a dice, and if I ask you what is the chance that a prime number has appeared, what will you say? It is half, right? Because there are 3 possibilities of prime numbers out of the 6 total thing. But suppose I tell you I rolled a die, I have seen the outcome, and I will tell you that the number on the top is an odd number. Now what will you tell as the don't use any formula, but what is the probability of that number being a prime number? Can you guess? Yes. Dharani? Any guess? It's simple, right? I'm saying you that I have rolled a dice. I'm not telling you any information, and I'm asking you what is the probability that the number on top is an prime number. So you will tell me what is the answer you will give me. You will give it is 1 by 2, right? Is that okay?
Yes, sir.
Yeah. Now suppose I tell you that I rolled a dice and I know that, and I tell you the extra information that the number on the top is an odd number. Now, will you think of 2 being an outcome? You will not think of 2 being an outcome, right? Because I've already told you that the number is an odd number. So what are the possibilities?
3
The
and 5,
possibility,
sir.
yeah, only 3 and 5. So there are 2 outcomes. And what are all the possible outcomes? It is just 1, 3, and 5. So if I tell you the extra information that the number on top is an odd number, then the probability that you assign to the event A, given this extra information about the event B, is different. So P of A condition B is different from P of A. If I give you this extra information that B has occurred, then you know that there are some outcomes in the sample space which cannot have occurred, right? So if I tell you it's an odd number, you know for sure that the number is not 2, the number is not 4, the number is not 6. So this we just got by analysis. We just had 6 outcomes, and this you can do it by analysis. But if you have bigger samples, you need some formula. And that formula is what I said. P of A condition B is nothing but P of A intersection B divided by P of B. Now, what is A intersection B? A intersection B in our case, it is 3, 5. And P of B is, so P of A intersection B is the number of outcomes in A intersection B, which is 2 by P of S. Number of outcomes in S. So that is 6. So this is 1 by 3. Just a minute. Yeah. So P of A intersection B is 1 by 3. P of B, we already found it as 1 by 2. So 1 by 3 by 1 by 2 is 2 by 3. So this is to do this conditioning thing in a systematic manner, we have this formula. That's all. So if when we are given some extra information, we call it as conditional probability. If I know event B has occurred, then what is the probability of occurrence of event A? So that we call it as conditional probability, and we denote it by this symbol. And to calculate conditional probability, this is the formula we use. So is that okay?
Yes, sir.
Yeah, thank you. So that is the thing. So, but only the important thing you need to note is that since we are doing this division, the denominator cannot be 0. So P of A should not be 0. P of B should not be 0 in these 2 cases. That is important. So you cannot say that for the example I said, I say event A is a prime number appears on top. If I say event B is a number greater than 6 has appeared on top, we know the probability of event B occurring is 0. I can't ask you the probability of A condition B has occurred because B cannot happen. So that is just common sense. So P of B and P of A has to be possible events. They should have a positive probability. Only then we can do the division. Now, if A and B are independent, then whether I tell you say if A and B are independent events, then the occurrence of B should not affect the probability of A, which means P of A should be just equal to P of A condition B, and P of B should be equal to P of B condition A. So the occurrence of B does not affect the occurrence of A. So in that case, those 2 events are said to be independent events. And when the events are independent, so if you just substitute in this, right? So when is P of A condition B equal to P of A? In that case, when do we get it? So that happens when P of A intersection B is equal to P of A multiplied by P of B. So this is the mathematical, this is the corollary. This is like, if events are independent, then their probabilities should obey this. And what is independent? The occurrence of one event does not affect the probability of occurrence of the other event. So if I say the example for independent events, I can say, so here these 2 events are clearly not independent, right? because P of A is not equal to P of A condition B. But I can, if I say you're tossing two coins and event A's head appears on first coin and event B is head on second coin. By common sense, you know that they are independent events, right? It cannot affect each other, but we can also prove it mathematically. So for this, the outcomes in the sample space are what? We can have head on the first coin, head on the second coin, head tail, tail head, and tail tail. What is the event A? It is head on the first coin, so it is head head and head tail. Event B is head on the second coin, so it is head head and tail head. What is P of A? It is 1 by 2. 2 by 4, it is 1 by 2. P of B is 1 by 2. Again 2 by 4. What is P of A condition B? It is P of A intersection B divided by P of B. What is A intersection B? A intersection B is the singleton set head head. So that is the only common thing, right? So what is P of A intersection B? P of A intersection B, it has one outcome and sample space has 4 outcomes. So it is 1 by 4 divided by P of B is 1 by 2. So this is again 1 by 2. Similarly, P of B condition A is also 1 by 4 divided by P of A is also 1 by 2. So it is 1 by 2. Note that this is equal to P of A and this is equal to P of B. So the occurrence of event B does not, those two coins are two different coins, right? So one coin cannot influence the other. So this also follows mathematically. Now you see P of A intersection B is what? 1 by 4. That is just 1 by 2 into 1 by 2, which is P of A multiplied by P of B. So this also follows this. So whatever we expect based on common sense, you put it in a mathematical form that becomes the definition for independence. So it's just that P of A so if two events are independent, if and only if P of A intersection B is equal to P of A times P of B. Now let us go back to this problem. It is given that these two events are independent events. A and B are independent events. So what is P of A intersection B? P of A intersection B is, we know the multiplicative law. It is P of A condition B times P of B. But if A and B are independent events, the occurrence of B cannot affect the probability of A. So this is nothing but P of A times P of B. What is P of A? It is 0.5. It is 0.8. So this is something like 0.4. Therefore, P of A union B. What is the probability of occurrence of at least A or B is 0.9. And whatever value we get there, that should make sense. It should be less than 1 and it should be greater than 0. Sorry, less than or equal to 1 and greater than or equal to 0. So the answer to this correct to 1 decimal place is 0.9. So this is, I think, gate, this is question 26 of gate 2023. Asset 1. Asset 1. So this brings us to kind of basic definitions and all we have completed in probability. This is just useful for solving problems. So what are permutations and combinations? If you think, again, this is a high school level thing. So, you know, it is just systematic counting. It's just systematic counting of the possibilities. These are very useful in solving probability problems. So suppose we are given n different things and all are taken at a time. How many permutations are number of arrangements, right? Number of different ways you can arrange. Ways to arrange. So again, these are very basic. So if you have A, B, C, D are 4 different things, you know, you can arrange them as A, B, C, D, A, B, D, C, and so on. So basically you have 4 spots and without repetition, you have 4 chances here. Whatever you have put here, you cannot put here. So you have 3 chances here. Whatever you have put in these 2 places, you cannot put here. So you have 2 chances here. Whatever you have put in these 3, you cannot put here. So you have 1 chance here. So the number of ways to arrange is 4 into 3 into 2 into 1. So the number of ways of arranging n distinct items, that's all. The number of ways of arranging n distinct items is n factorial without repetition. If you are allowed to repeat, say you're allowed also to have A, B, and so on, then there is no whatever you have used here, you can reuse here. So in that case, with repetition, the number of chances for this spot is 4, here 4, here 4, and here 4. So it is 4 power 4. So if repetition is allowed, then it is n power n. This is with repetition. Now quickly, you can also specialize it to the case where you're not arranging all the n items, but you're only arranging k of the items. So suppose you have 3 places. You can only take 3 letters and arrange them. Then you just strike off the last. So you have 4 into 3 into 2, which is n factorial divided by n minus k factorial. So k is 1 in the k is 3 and n minus k is 1. So n factorial is 4 into 3 into 2 into 1 divided by 1. And if you strike out another, if you just have 2, it is just 4 into 3. You cannot have two, these two places do not exist. So the number of ways to arrange k of the n items without repetition is n factorial by n minus k factorial, and this has the special symbol npk. And this is not important, this alone, this you can remember. And again, with repetition, it's very easy. Suppose you are given just 2 blanks and 4 possibilities for each blank, then it is 4 power 2. So it is just n power k. So we already got 4 of these answers. So in this permutations combinations, the number of ways of arranging n distinct things all taken at a time is n factorial. And if you are arranging only k of them, then it is n factorial divided by n minus k factorial. And if you allow repetitions, it is n power k, where k is the number of items you are choosing at once and n is the total number of items. Now suppose there are m classes of equal things among them. So suppose instead of A, B, C, D, I'm given A, B, C, A, and I have to arrange it in 3 places, or fine, you just have to arrange it in 3 places. Then the number of ways you can arrange is, if you put a 1 here and 2 here, right? You call this as A1 and A2, treat them as different items. So you can arrange them in NP k number of ways. If you treat these two A's as different, you can arrange them in NPK number of ways. But the problem is this A is the same as this A. So how many ways you can arrange this itself? You can arrange this, suppose C of them are repeated, then you can arrange that itself in C factorial number of ways. So you can take only the A's and you can either put A1 here and A2 here, or you can also have A2 here and A1 here. These two are counted as 2 distinct possibilities while taking the number of all possible arrangements, but they are actually the same. So you divide by that. So you have 2 of them, right? So you just divide by that. So divide by C factorial. So if there are m classes of equal things among them, so totally you have n items, and among the n items, you have n1 items are same, n2 items are same, and so on up to nm items are identical. So you think of it this way, you have a basket of 20 fruits, and out of them 4 are apples, 6 are lemons, and 10 are bananas. So the number of distinct permutations, and all these are the fruits of the same kind, are identical. There's no difference. So the number of different permutations you can come up with is not 20 factorial right? It's not 20 factorial because a lot of them will be repetitions. And these repetitions, initially, how do you treat them? You think of them as banana 1, banana 2, banana 3, and so on. Apple 1, apple 2, apple 3, and so on. Initially, you put a tag on each of the fruit and then you arrange them in all possible ways. Then while you remove the tag, you see that however you arrange the bananas among themselves and the apples among themselves, they all correspond to the same permutation because they are all identical. So if there are m classes of equal things among them, then it is npk divided by n1 factorial, n2 factorial, and so on up to nm factorial. So you first arrange k of the n in all possible ways, putting a tag on each of the member. But then if you have identical members, it's the same, right? What I just said. If you have A, B, C, A, you can have only one permutation, which is A, B, C, A. But that is difficult to do it in the first step because we don't have a direct formula for repeated items. So in case of repeated items, you assume that this A and this A are different. Put a 1 here and put a 2 here. We don't do this while solving problems. It's just that in case you forget the formula during gate, you should be able to derive it, right? If you have enough time. So you put a 1 here, you put a 2 here, arrange it in all possible ways, and then make use of the fact that even if you interchange A1 and A2, in whichever way you arrange A1, A2, A3 among themselves, it is not going to change the global permutation. So just divide it. They're all identical, so just divide it. So if there are m classes of equal or identical things out of the n things, then you divide it by n1 factorial, n2 factorial, up to nm factorial. So then the last one is combinations. So this basically follows from this. Combinations, in case of combinations, the order is not important. So it only, you know that very well. So whether you have A, B, C, D or A, C, B, D or A, D, B, C, you can put all of them correspond to the same combination. You can arrange this in 4 factorial number of ways. Sorry. Yeah, you can arrange this in 4 factorial number of ways, but all of them have the same entities. So the order is not important. So when order is not important, for example, same the fruit basket example, if you take, you just want to see what combination of fruits you want to eat for the dinner. It doesn't matter whether you take lemon first, then apple, then bananas. So, and the combination is not important, the order is not important. It only matters whether you take apple and banana or apple and orange or something like that. So when the order is not important, all the permutations of consisting of the same entities are identical. So when the order is not important, you call this as NCK, the number of combinations of of n items k taken at a time. So totally are given n number of fruits and k of them we are taking at a time. And the order in which we take them is not important, which means how many ways you can arrange the permutations. There are k factorial. Right? So similarly, just follows from this. It is just npk divided by k factorial. So it is n factorial by n minus k factorial into k factorial. So these are, with this, I think gate. So all these drawing something from a lot with and without replacement, all of those problems in gate are based only on these concepts. We don't need to know anything more than these three. If at all anything is required, that can be derived easily, but these are the basic things. If you have n distinct things all taken at a time, n factorial, k of them taken at a time, it is npr, which is defined this way, npk, which is defined this way. And if there are certain things that are repeated, divided by the number of repeated factorials, say. For the fruit basket example, let me put it for the last thing. So we have 20 fruits, 4 apples, 6 bananas, and 10 guavas. So if this is the case, the number of, and all are identical. All apples are identical, all bananas are identical, all guavas are identical. then the number of ways to select 3 fruits. So number of permutations of say 3 fruits is 20p3 divided by all apples are the same, so 4 factorial. All bananas are the same, so 6 factorial. All guavas are the same, so 10 factorial. You can also have non-repeated things. In that case, you just have to multiply by 1 factorial. So that is not. So if you have plus 1 orange and 1 pineapple and so on, the denominator just keeps going on. It is just 1 factorial, 1 factorial. So, but these are all 1, so I don't need to write them explicitly. So yeah, so this, if you simplify, it is 20 factorial by 20 minus 3 factorial, so 17 factorial, 4 factorial, 6 factorial, factorial. Just a minute. So sorry, this holds only if you take all at a time. So it's not, so you cannot do it for 3 fruits. You can only do it for all fruits. So it is 20p20, which is 20 factorial divided by 4, 6, and 10. Otherwise, you'll get something less than 1. So that is not possible. In every case, for every, if you're choosing k out of them, you cannot use this. So sorry about this. This is when it's not NPK. If m classes are equal among them, this m means all taken at a time. So it is just n factorial by n1 factorial, n2 factorial up to nm factorial. So that's all. Don't take the NPK thing because each of the permutations don't have n1 number of apples. So that's incorrect. So take n factorial by n1, n2, nm factorials. So the next topic is random variables, but it's almost time. We are past time. Maybe next week I can continue from this point, random variables. The other 2 problems that I decided for today are basically from random variables. That's an important topic in GATE that has got repeated questions. So maybe we'll take it up in the next class. I'll wait. If you have any doubts, you can ask me. If you have any suggestions, you can provide. And also, I don't know if you are attending this for the first time, you can join this Google group, groups.google.com. Let me put it in concrete. So groups.google.com. Oh, okay. So this, you can type this NPTEL GATE hyphen C 2023, this thing, and you search in all groups. So this one comes up. This is a group that I have created. This is all these presentations, solutions, and the video recording I will be uploading to this. You can join this. Let me paste the group link in the chat box. You can join this if you have any suggestions, if you have any comments or any kind of feedback also, if you want something, or even within the week, if you want any doubts to be clarified, you can post it there. Any question, any particular question, any difficulty, you can post it there. I will respond. So let me wait for some time. If you have any doubts, you can. Is everything okay? If you can say me if you have any doubts.
Understood, sir. Thank you, sir.
Okay. Thank you. Thank you for attending. Can. I'll wait for a while. You can go through this. If you have doubts, you can stay back. Otherwise, you can leave. I'll end the session. Okay, I'll upload the recording. Thank you for joining. It was a good session. We'll see next week, Monday. Let us continue probability. Then we can look at traffic engineering and maybe hydraulics, channel hydraulics. Thank you.